that memory where we have the information that we usually use and we operate with, and we have, you know, the huge memory. And in your case, you didn't have the information in the cache, assuming it was somewhere in the operating memory. Okay, then in here, I'm using 2 inverters per cell plus some kind of, you know, addressing structure. And in here for the DRAM, I'm using 1 transistor per location. Even though you are computer engineers, or you will be computer engineers or embedded system engineers, it's not bad to understand the technology. At least to have an idea what's behind there. Now, this aliasing is something that I have to deal with. And one way or another, I have to find a solution, because otherwise I'm not operating with a cache. The selection of the bits that I'm choosing will determine the way this aliasing happens. Then if I'm choosing those 4 bits here, let's say the least significant bits, I will have locations which are going modulo 16 in the same position. If I'm choosing somewhere here, the scrambling will be different. And I also can choose 1 bit here, 2 bits here, and another one here. Nobody precludes me in doing that. The only thing which I have to be sure is that I'm using the same bits all over the place. Because if in one place I'm treating the address in a way and in another place in a different way, I'm not getting the information that I'm looking for. Now, because I have this kind of aliasing, I can try to find a solution to deal with it. And the solution is by increasing what we call associativity. Then, in this design, what I assume is that for a certain address, I'm bringing, you know, a data line of caching here, starting from this location, or from this location, or from this location. Now, all those locations cannot stay in the same time in the cache. It's one or another one, not 2 of them, or 4 of them, or 8 of them. But I can think now about a different concept, which is called associativity. What I do is I make an investment. And the investment will be to make the cache, let's say, twice as wide. Then in the same address, I will create room for 2 items. Then if I have, let's say, this one and I'm bringing it to the cache, I'll put it here. If there is this one also coming, if I don't have that mechanism, that one will have to replace what I have here. Instead of replacing, what I'll do now, I'll say, okay, this one will go in this. Again. Thing. And I can now increase the capability of the cache to deal with aliasing. This and this will be able to exist, to coexist in the cache. But the price is that I double plus or minus the capacity, not line-wise, those are called sets. Then in this case, because I have this, I have 16 sets. And initially, in each set, I had the possibility to store 1 cache line. Now, because I double the capacity, I store 2. And I can think also about storing 4, or 8, or 16, or whatever. Now, you may say there is a complication. Sure, there is a complication. I did not tell you how I actually know whether or not a certain location is in the cache or not. I'll have to deal with that now, even in another direction. It's not only that I have to know whether what I'm looking for is here, but I have now to check whether it's here or here. Then the processing which is associated with this mechanism will get even more complex, but will help me to deal with this aliasing in a kind of nicer way. Now, how do I deal with this thing? This is now the real overhead of the cache. You see, I used some bits which we call the index in that's the address. I'm actually looking for a location in the main memory which is in the position at that address. And in my case, this is a 10-bit address. Out of those, I choose 4 bits, which in here are called the index. And I use those index to look in the cache and to see whether or not the data that I'm looking for is present there. Now, there are 2 other parts of the address. One refers to what is called the offset. And this is telling me which position in the cache line I'm looking for. I assume that in this case I have 2 bits which will select me this or this or this or this. Those are words like in the architecture of my system. That will allow me to select the right one because I'm looking for a word. I'm not looking for 4 words. But I still don't know which location is present in the memory. Now, in order to do that, in the cache, whenever I bring information from the main memory, I will store the data, but I will also store what we call a tag. A tag is the rest of the bits which I'm not using for index, neither for offset. Now, when I'm taking the index and I'm looking in this set, what I have to do is I have to compare the tag in my address with the tags that I stored in the memory. Assuming that I have only simple cache, which we call direct map cache, then there is only tag data, the first 2 columns. What I have to do is take the tag from the address, take the tag from the location that I'm selecting in the cache, compare them, and if they are the same, the information in the cache is the one that I'm looking for. If they are different, it's not what I want. Now, assuming that I have associativity, I have to compare the first and the second. If I have 2 ways. If I have 4 ways, I have to do 4 comparisons to see which of the tags is the one that I'm looking for, if any. Because there is also a chance that the location that I'm looking is not there. Now, then when I address the cache, I'm issuing the bits for the selection. I select the set, and depending on the associativity, I have to make 1 or more comparisons in parallel. If one of the comparisons will give me a yes, then I'm happy, I hit the jackpot. Then my information is there. If none of them will give me a fit, I'm not happy. The information is not in the cache, and then the processor has to stall or do whatever is possible, and then the cache, actually somebody which we call the cache controller, will start bringing the information from the main memory into the cache. This process is transparent to the CPU, in the sense that the CPU is not involved in it. But from the time point of view, this process may hinder the performance. Now, those comparisons I can do in parallel or I can do sequential. If I do sequential, I'm blowing the cycle time. Then what I want is to have parallel comparisons. Now, one thing that I didn't tell you is that somebody has to load the tag. Then whenever I have a miss and I'm looking for information in the main memory, the cache controller will bring information from the main memory and will also update the tag. Okay? Now, assuming that I have two sets for the memory and I do not find the information there, I have another question. Which of the two I should kick out? You know, because I can kick out the first or the second. I have to bring new information because this is what I want. First or the second should go out. This is what is called replacement policy. If I'm not doing a good selection on that, I may kick out whatever I will be needing in the next cycle. And then, you know, tough luck. Life is misery, or not? Now, this is exactly what I told you. Then I'm using here 4 bits for the block. Then I have each block contains 4 locations, and if I do those div and mode, you know, those are related to integer division, they will give me the block where I am and the position where I am, assuming that I am doing the split of the bits in this way. This is traditionally the case, but as I said, this is a convention, and you can use it in a different way. Actually, you may also want to play with this in order to bring information in the same line, which are not really consecutive in the memory, because what the cache is doing is saying, you know, I'm looking for this, and I'm loading this and the next 3. If I play with a different kind of, you know, memory selection, I may bring this, and this. This may make sense to me in some cases. Do you have idea when will be nice to have that? This is what is called stride addressing. If I deal with a matrix, which is stored in, let's say, in a certain way, like row-wise, let's say the matrix has 4 elements per row, and I want to get the elements column-wise. Each location in the column will be modulo 4 away from the previous location. Then if I want those to be consequent in my main memory, in my cache, I can use such a mechanism of bit scrambling. Again, do not get the idea that this is a standard approach. The standard approach is whatever you see there. But in a special purpose system, where I have this kind of tricks, I can actually switch the scrambling of the cache depending on how my memory is stored and what I want to do. And that will perform in a different way. But those are, let's say, advanced tricks. Okay. Now, the previous slide is just an explanation for this one. Then I will just tell you on this. Then basically this is summarizing. Guys, are you playing with the computer? I'm just curious. What are you doing there? Writing a report for another course? No. Wrong guess. Am I disturbing you in any way? No. Okay. I'm very happy you are tolerant. Then, I have 2 extremes. One is my initial story. Each location will map into one possible location in the cache. Then I have no freedom whatsoever. I take the bits, and based on the bits that I'm using as address, location in the main memory in address A will always go into A prime in the cache. And this is direct mapped. No freedom, no way. If all my addresses will actually map into set 0, the rest of the cache might be empty, and I will keep on replacing people, data from set 0. Then I'm just using a set, the rest is empty. Now, this is simple and fast, no flexibility. At the other extreme is everybody can go everywhere. Then instead of having 8 sets, like in here, I have 1 set only. Then there is no addressing to the cache. Everybody can go everywhere, which means that in this vector, I am storing the complete address and the data. And I have the freedom to put in my cache 8 locations regardless of their addresses. I will have no address contention. There is no aliasing because there is no addressing. If I get 8 items, I put them there. And I have the compromise. Not full flexibility, not zero flexibility, somewhere in between. Now, why would I not go for full flexibility? Okay, I'll answer myself, right? It's too early for me. Because the full flexibility will have a very big overhead. I will have to memorize for each location the complete address, all 10 bits, and the data. While in this one, I will have to memorize 6 bits per location, assuming that we are in my example with 10 and 4. Then this will cost me a lot in overhead. And also there is something else. I have to do 8 comparisons in parallel. Then in here, I just compare 1 tag. In here, I have to compare 2 tags in parallel. In here, I have to do 8 tags in parallel. And if I have a memory which is somehow larger, because 8 sets like here, actually 8 sets are 3 bits, right? But you are not yet awake to jump and to say, no, you're wrong. Or you don't dare to say that. In Dutch culture, you should dare that. In Far East cultures, the professor is always right, regardless of the stupidity that he or she just said, right? True? Which one is the right one?
The first one.
What do you think? You've been in East and you've been also in the Netherlands for some time. Which one do you think?
Dutch way, I think is better. Dutch way.
Dutch way, okay. I think the same. Nobody is always right. And it's good to, to comment. Then, this is beautiful, but it costs me a lot. And in practical cases, I cannot really implement it. Assume that I have, I don't know, a couple of kilo location cached. I'll have to do a lot of those comparisons in parallel. Okay. Now, we kind of discuss about block identification, then the fact that I'm issuing the address, I'm making the comparison, but there is a small detail which I didn't speak about, which is a bit in the cache line, which will tell me whether or not the information there is correct. And this is the valid bit. Why do I need a valid bit? At the beginning, I may start with a certain state of the cache which belong to a previous application. And then if I look in the cache, I may have data which is there, you know, my address will be good, my tag will be good, and I'm bringing information which is not mine. Then in order to avoid that, when we start, all the lines in the cache are not valid. They are validated by the controller whenever in the execution I'm bringing information in the cache. Also, I may use that valid or not valid cache to invalidate the content of the cache line whenever that one is not really representative any longer. When might such a situation happen? Again, I'll answer the question myself. Okay, I don't want to stress you today, it's too early. If I have more clients for the main memory, each one of them having its own cache, and I'm working on parallel on those, maybe the copy in my cache is not the last value of that memory. Maybe some other process or processor made a change on that variable, and then I don't want to have two copies which are different on that variable because my program will go bananas. And then there is a protocol going on, this is towards multi-core kind of processing, which will be saying, no, 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 your copy is not good. I have a better one. And this may work in the sense that I'm transferring from one cache to another, or I'm just invalidating, and whenever I'm looking for, I'll bring it from the main memory. Then, having said that, you have the big picture of the cache and how it works. Then, this is an example with 32-bit address, out of which 8 are utilized for the index in the cache. Then I have 256 locations in the cache. This is a 4-way cache. Then per each set, I have 256 sets because I have 8 bits for index. Then what is happening is that I'm issuing the 8 bits to the cache. And then because of the value which is there, I'm selecting the one which is gray. Now this one now has 4 sets, and all of them will be going for output, potentially. I don't know yet which one will be. One of them or none of them. But all of them, all 4, will go for output. Then I can see this like a word which is 4 times the architecture size of the word. Now I'm doing 4 comparisons, and those comparisons now are on 22 bits, because those are the bits which are part of the tag. And I have 2 other bits which will let me select what item I want from the cache line. Then the cache line has 4 items, there are 256 sets, and there are 4 ways. I'm making the comparisons, and now each comparison will give me a certain result. The comparison is one thing, but the result of the comparison will be really true only if the valid bit is 1. Then I'm also going with that through an AND gate. If the valid bit is 0, no way. Then if one of those comparisons will give me a hit and the valid bit is 1, this gate will provide me a signal which will say, I have it for you. I'm lucky, I can offer you whatever you are looking for, and because what I want is one of those, I have to do a selection with a 4-to-1 multiplexer. Now, because selection is done with powers of 2, we don't have 5-way associative cache. because 5-way associative cache or 7-way associative cache or 8-way associative cache will require the same amount of bits for selection. They will use less comparators, but it's not really making sense to have that kind of weird things. Why are you not saying you deserve a break?
Nice topic.
You get the right for a break, right?
Yeah.
I owe you 3 minutes. Oh my God.